Hello and welcome to Inside Wi-Fi, Video 9. Effective Inverse Square Law on RF Propagation. In the last video, we learned that radio signals become weaker as they travel through space, a phenomenon known as free space path loss. But what causes this signal reduction, can you imagine? The answer lies in a principle known as the inverse square law. What is inverse square law? The inverse square law is a fundamental principle of physics that describes how the strength of a wave or force decreases as it spreads out from its source. In RF propagation, it states that the power density of an electromagnetic wave decreases in proportion to the square of the distance from the transmitter. Power density is inversely proportional to the square of the distance from the source. In essence, the inverse square law is a fundamental principle that explains how RF signals weaken as they travel through space. Understanding this relationship is essential for predicting signal coverage, calculating path loss, and designing reliable wireless communication systems. Wi-Fi signal intensity and distance. As electromagnetic waves carrying RF energy are transmitted from the antenna of a wireless access point, they propagate outward in all directions. Some of this energy is captured by the receiving antenna of a wireless client device such as a laptop, smartphone or tablet. As the signal travels farther from the access point, it spreads over a larger area, causing the signal power density to decrease according to the inverse square law. Consequently, the wireless client receives a weaker signal as the distance from the AP increases. This reduction in signal strength can lead to lower data rates, reduced coverage, and a greater likelihood of transmission errors. For this reason, the distance between a wireless client and an access point is one of the most important factors affecting Wi-Fi performance. Received signal strength and distance. The Received Signal Strength Indicator, RSSI, measures the strength of a wireless signal when it reaches a client device. Generally, the closer a device is to the wireless access point, AP, the stronger the received signal and the higher the RSSI value. As the distance between the client device and the AP increases, the signal spreads over a larger area and loses strength. As a result, the RSSI decreases, indicating a weaker received signal. This reduction in signal strength occurs due to the natural spreading of electromagnetic waves in space, commonly described by the inverse square law as well as other RF propagation characteristics. A stronger RSSI typically results in more reliable communication, higher data rates and better overall Wi-Fi performance. Conversely, a weaker RSSI can lead to reduced throughput, increased packet retransmissions, and potential connectivity issues. Signal strength decreases with distance. Consider a transmitter radiating RF energy uniformly in all directions. If the power density is 1 watt per square meter at a distance of 1 meter, then according to the inverse square law, at 2 meters, the power density becomes 1/4 watt per square meter, at 3 meters, the power density becomes 1/9 watt per square meter, at 4 meters, the power density becomes 1/16 watt per square meter. This occurs because the same amount of transmitted energy is spread over an increasingly larger area as the signal moves away from the source. As a result, the signal becomes weaker with distance. At 1 meter distance from source, the relative power density is 1 watt per square meter. At 2 meter distance from source, the relative power density is 0.25 watt per square meter. At 3 meter distance from source, the relative power density is 0.111 watt per square meter. At 4 meter distance from source, the relative power density is 0.0625 watt per square meter. This example demonstrates that when the distance is doubled, the power density drops to 1/4 of its original value. Consequently, wireless devices located farther from an access point receive weaker signals, resulting in lower RSSI values and potentially reduced network performance. Consider an access point transmitting at 500 milliwatts. The only place we could measure 500 milliwatts or 27 dBm would be directly at the antenna of the access point. If we consider a typical Wi-Fi client device and look at the RSSI of the access point at 6 meters distance, it may measure something really strong like -50 dBm or 0.00001 milliwatts. As you move further away from the access point, the RSSI continues to drop. When you reach 12 meters, you would expect to only see 1/4 of the radiation that you saw at 6 meters, -56 dBm or 0.0000025 milliwatts. If you travel out to a distance of 18 meters, at 3 times your initial radius, and you expect to see only -59.5 dBm or 0.0000011 milliwatts as RSSI. That is about 1/9 of the intensity measured at 6 meters. Impact of inverse square law on RF systems. Reduced signal strength, lower RSSI. As distance from the transmitter increases, the received signal strength decreases rapidly. Reduced coverage quality. Devices farther from the transmitter experience weaker signal levels, less reliable communication, increased susceptibility to interference and noise. Lower data rates. Modern Wi-Fi systems use adaptive modulation and coding. When RSSI decreases, higher order modulation schemes, 1024 QAM, 256 QAM, etc., become unusable. Devices fall back to slower modulation rates. Maximum throughput decreases. Increased packet retransmissions. Weak signals are more likely to be corrupted by noise, leading to frame errors, packet loss, and more retransmissions. Retransmissions consume airtime and reduce overall network efficiency. Reduced signal-to-noise ratio. As signal power decreases while background noise remains relatively constant, SNR decreases. Receiver sensitivity becomes a limiting factor. Decoding errors increase. Antenna design. The design of an antenna is critical in overcoming the limitations imposed by the inverse square law. High-gain antennas can concentrate RF energy in a specific direction, effectively boosting signal strength at the receiving end. Signal processing. Advanced signal processing techniques help reduce the impact of signal attenuation caused by the inverse square law, improving communication reliability over longer distances. Let me know your thoughts in the comments if you found this video informative and helpful. In the next video, let's see about antennas in Wi-Fi. Thank you for watching.